Welcome to the second part of lecture 19. In this second part, we are going to build on what we introduced in part 1, meaning the concept of expected values, and we are going to introduce the expected value theorem, and we are going to show how to use it on a couple of example problems. After that, we are going to cover a number of practice problems from the area of combinatorics as well as probabilities. Solving these problems will help you to do well on the quiz that will involve these concepts. So let's get started with the expected value theorem. So the expected value theorem goes as follows. Suppose an experiment consists of the independent repetition of a trial n times, and the probability of that trial's individual success is p each time it is performed. If x denotes the number of successful trials in this experiment, then the expected value of x is equal to n times p. In the slides here, I also give the proof for this theorem, which is done using the technique we already saw when we were doing proofs called proof by induction. So feel free to study this proof. I'm not going to go over it in the lectures. So it's not critical to understand it to be able to solve the problems. So here is the continuation of the proof. And here is the first example problem where we are going to try to apply this theorem. So a softball player gets a hit with probability 3/5 each time she steps to the plate. In any given game, this player has exactly 5 plate appearances. So we're going to set this up by selecting our random variable x to be number of hits per game. So we first have to determine from which set can the values of x come from. And this set includes values 0, 1, 2, 3, 4, 5. Because there is 5 appearances, and those are the number of hits per these 5 appearances that we can expect. Now, we can compute this starting with Bernoulli trials, which is something we've done before. So we can compute the probability for x being 0, which is when there are no hits, and the probability for that is choose 0 out of 5 times 3/5 to the power 0 times 2/5 to the power 5, because they're all misses. And this is what this computes into. And we can do similar computation for all x's from 0 to 5. And then we know, once we have that, we know how to compute the expectation for x is 0 times 32/3125, which is just 0, so it's not included here. And then 1 times 0.077 plus 2 times 0.230, and so on. And we compute this expression, we get 3. Now clearly this was quite a lot of work. And now the question is there a quicker and easier way to compute t of x? And as it turns out, there's a really simple way to do it using the theorem we just introduced. So in this setting, n is 5, and p is 3/5. And then as per the theorem, expected value of x is 5 times 3/5, which is equal to 3. So we can leverage this theorem to save us a lot of computation time, as you can see from this example. Okay, so let's look at another example. Suppose teams A and B play a best of 7 series, meaning they play until a team has won 4 games. And team A has a probability P of winning any given game. Given that the games are independent events, what is the average number of games played in terms of P? So here we are not given a concrete value for P. So what we want to do, we want to express the expected value of X in terms of P. And X here is the average number of games in a series. And so again, we have to determine from which set can X be drawn. And in this case, it's from the set 4, 5, 6, and 7. And then we compute our Bernoulli trials. So when there is 4 games, the probability of the series ending in 4 games is p to the power 4 plus 1 minus p to the power 4. So this is the setting that we've seen in the previous part 1 of this lecture, where we have either 4 A's, which is p to the power 4, or we have 4 B's, which is p to the power of, which is 1 minus p to the power 4. If it finishes in 5 games, then we have this configuration. These 2 configurations. It's either this or it's this. And so on the left, A wins. So we have to place another 3 A's in these 4 slots. And then probability is p to the power 4 times 1 minus p. That's captured by this first expression. On the right is when B wins. So again, we are choosing 3 slots out of these 4 to place B's in. And the probability is 1 minus p to the power 4. Those are the 4 B's times p, which is 1A, when A won. And the similar reasoning applies to the other probabilities for X is equal to 6 and 7. And then the expected value for X is 4 times probability when X is 4, 5 times probability X when X is 5, and so on. Which, note that P is in this case symbolic, it's not a concrete value. So it evaluates to this long expression when we multiply everything out. Okay, so once we get that, one nice thing that we can do is that we can plot this expected value for X against the probability P of team A winning the game. And so this is the graph that we get. An interesting point in this graph is, for example, when the probability is 0.5, then the expected value for X is 5.8 games. Of course, as the probability for P increases or decreases, the expected value for X is also going to decrease, because one of the teams is more likely to win in less games. Okay, let's look at another practice problem. So let's suppose a 3-person committee is formed for a club by drawing names out of a hat. If the accepted number of women on the committee is 2.0 and there are 10 men in the club, then the question is how many women are in the club. So we can solve this by setting X to be the number of women on the committee, and we know that the expected value of X is 2.0, and we keep the number of women in the club to be symbolic, because that's what we are trying to discover. That's what we're trying to compute. So if we compute E of x, we get that it's equal to 0 times probability of x being 0, plus 1 times probability of x is 1, plus 2 times probability of x is 2, plus 3 times probability x is 3. If we actually compute this, the first one, of course, just disappears because that's multiplication by 0. And the second one is equal to 1 times. And what is the probability that we have one woman on the committee? Well, the total number of committees, which is here below, we get it by choosing 3 people out of 10 plus W, 10 plus W, where 10 is the number of men in the club and W is the number of women in the club. And how many of this total number of committees have one woman? Well, it's choosing one woman from W women in the club times choosing 2 men from 10. So this is what gets us, this is the expression when x is 1. And we can compute x is equal to 2 and x is equal to 3 in a similar fashion. So once we plug in the definition of choose, this is the expression we get. And then we can simplify this further, and finally we end up with this expression. So the expected value of x is equal to 3 times W divided by 10 plus W. And so now to compute W, we can plug in 2 instead of expected value of x. We get 2 is equal to 3W divided by 10 plus W. We are looking for W, so we have 20 plus 2W is equal to 3W, which means that W is equal to 20. So when there are 20 women in the club, the expected value for x is going to be 2. We can also plot this. On the x-axis, we have the number of women in the club. On the y-axis, we have the expected value for x, which is the number of women on the committee. And we can see then that they meet at 2. Okay. So these were the problems that I just covered that were related to expected values and the expected value theorem and so on. From now on, I'm going to do a number of refresher problems covering counting and simpler probabilities and so on. So one thing I definitely suggest you should do is try to solve all of these on your own before you proceed to watch my solution. So, pause your video now, try to solve this on your own. You should know by now how to solve all of these, and then take a look at my solution. Okay, so let's start with the first one. How many positive 4-digit integers are there? How many positive 4-digit integers use the digit 7? And how many positive 4-digit integers use the digit 7 or are even? So let's look at the solution for the first one. How many positive 4-digit integers are there? The solution is we have 9 possibilities for the first digit. Why is that? Because 0 cannot be at the first place. And then 10 possibilities for 3 other digits. And we use our rule of products to get 9,000. Part B, how many positive 4-digit integers use the digit 7? So we can compute this using our rule of complement. So how many positive integers do not use the digit 7? This expression computes that. So at the first place, we cannot have 0 and 7. So there is 8 possibilities. And the second place, we cannot have 7. Third place, we cannot have 7. Fourth place, we cannot have 7. And we have to subtract that from the total number of 9,000. And what we get is 3,168. Okay? Part C, how many positive 4-digit integers use the digit 7 or are even? So we can compute this using our rule of sum with overlap. So in this case, we can add up the number of them that use digit 7 with the number of those that are even, and we have to subtract from that the number of those that use digit 7 and are even, because those got counted twice. And so when we calculate this, we get 6,408. So how did we get with the number that we used, where we needed to determine how many positive 4-digit integers use the digit 7 and are even? We did this as a side calculation, and we did it using the rule of sums. So there are a couple of cases here. We have even integers that have 7 at the first place, even integers that have 7 at the second place, but not at the first place, since we already counted those. And then 7 at the third place, but no 7 at the first and second, and 7 at the fourth place. And how do we calculate those? Well, if 7 is in the first place, it means we have only one choice for the first place. That's 7. We have 10 choices for the second place, 10 choices for the first place, and we have 5 choices for the last place because the number has to be even. So it has to end in 2, 4, 6, 8, or 0. Okay? When 7 is in the second place, this is what calculates the number of outcomes. We have 8 for the first digit because it cannot be 7 or 0. We have a similar expression when 7 is at the third place, and when it's at the fourth place, that's not possible because then the number is not even. And so when we add this up, we get 1260, which is what we plugged into that final general rule of sums and computed the final result. Okay, so this was a pretty tricky counting problem. if you manage to solve on your own, if you manage to solve it on your own and got the correct result, good for you. If it's unclear how this works, please make sure to come to office hours. We'll gladly explain this to you in much more detail during office hours. Okay, more example problems. We'll do a lot of these. The key to do well in this class is to practice and solve a lot of problems. And try to solve them on your own. I will keep stressing this out. Pause the video, try to solve it on your own, and then try to follow my solution. Okay, so let's go through these one by one. How many ways are there to fill a bag of 11 pieces of fruit from a stand that sells 3 types: apples, bananas, and oranges? So we know our bag formula is C of R plus N minus 1, comma R, where R is the size of the bag and N is the number of types of things that we're putting in the bag. In this case, it's 3. And so when you plug in the numbers, you get C of 3, 11. When you calculate this out, you get 78. Now, as we showed in the lectures previously, the bag problem is related to the problem of counting different binary sequences. And so this question asks us, what is the binary sequence that represents a bag of 6 apples, 2 bananas, and 3 oranges? So if you remember how these are equivalent, zeros, the numbers of zeros are the counts of each of the 3 different types of fruit, and we use ones to separate those zeros. So this is the solution. We have 6 zeros for 6 apples, then 2 zeros for 2 bananas, and 3 zeros for 3 oranges. And then finally, this is also equivalent to that sum equation. And so what equation will represent a bag of 2 apples, 0 bananas, and 9 oranges? So this is the equation that represents it. So if you remember, it's x1 plus x2 plus x3 is equal to the size of the bag. Okay, let's look at more problems. So if 10 apples are distributed among 5 children, so that every possible distribution is equally likely, what is the probability that every student gets at least 1 apple? How do we go about calculating this? So what is our sample space? So our sample space is a number of non-negative integer solutions to the following equation. So because we're distributing 10 apples to 5 children. And again, we can plug in the same formula we used just now. In this case, R is 10 and N is 5. And so our sample space has 1001 outcomes, and they're all equally likely. Now let's look at our event space E. So event space E are all non-negative integer solutions to the following integer equation. How do we get this? Well, we have to give at least 1 apple to every student. So we know that this equation represents the original equation, except that all the x's have to be greater than 1. And so that's equivalent to saying that they're greater than 0, and they add up to 5. Again, we compute the number of these outcomes using our formula for these equations, and we get 126. And so on the probabilities, then 126 over 1001. So this is a nice problem that combines unordered lists or bags with probabilities. Okay. So this problem takes us back to counting. So the question is, how many distinguishable arrangements of the letters in discrete are there? So this problem is very similar to the problem that we had in the lectures on counting. I think it was basically the same, except there we had Mississippi, and here we have discrete. So how do we go about solving this? So in discrete, first we have to look for letters that are repeated. And the only thing that repeats are these two E's. So first we are going to place these two E's, and we have 8 positions we can place them. So that's going to be choose 2 out of 8. And then we place the remaining distinct letters in 6 unused positions, and that's going to be 6 factorial. And now we use rule of product. We multiply these two things, and this is the total number we get. So be careful when the letters are repeated. Then you have to place those first using this choose strategy, where you're picking the slots into which you are going to place them. Okay, more counting problems. So 50 runners compete in a race. How many outcomes are possible if we want to know how each runner placed? So in this case, we are looking at permutations of all 50 runners. So that's going to be 50 factorial. Part B, we want to see how many outcomes are possible if the 10 fastest runners qualify for another race. So in this case, we don't care about the order of these 10 fastest runners. We just want to choose 10 out of 50 because the order doesn't matter. And of course, there is no repetitions because the same runner cannot be twice in the set of 10 fastest runners. And finally, how many outcomes are possible if this is an Olympic event and we want to know who gets gold, silver, and bronze? So in this case, the medals are different. So the order matters and there is no repetition. So these are permutations. So it's P 50,3, which is equal to this expression. Okay, and now problem 2. You must answer 8 out of 10 questions on a quiz. In how many ways can you choose these questions? So the order doesn't matter, we're just choosing a set of questions. So you choose 8 out of 10. Now, what if you must answer the first 3 questions? So that means that for the first 3, we are choosing 3 out of 3, which is just 1. There is only one way to do that because we are forced to do the first 3. And then the remaining 5, we are choosing out of the remaining 7 questions. And part C, what if you must answer at least 4 out of the first 5 questions? Okay, so we have 2 situations here. So, or 2 cases. The one on the left is if we choose, because it says at least 4. So we have to choose either 4 or 5 out of first 5. This is the expression on the left captures the case where we choose 5 out of 5 first questions. And then we have to multiply this by choosing 3 out of the remaining 5. And the expression on the right captures the case when we choose 4 out of first 5, and then we choose the remaining 4 out of the remaining 5. And these are disjoint, and so we use rule of sum to compute the final result. Great. Okay, here is a simple problem on probabilities. So we want to determine what is more probable. A fair coin toss that comes up heads exactly 3 times in 6 tosses, or a fair 6-sided die that comes up as 5 or 6 exactly twice in 4 rolls. So let's compute these two probabilities. Again, pause your video now, try to do it on your own, and then compare your answer with my solution. So how do we compute the coin? So it's a fair coin, so probabilities of getting heads or tails are equally likely. And we're looking for configurations where heads come up exactly 3 times. So we are choosing 3 places out of 6 where we're going to place heads, and the probability of each one of these is 1 over 2 to the power of 6. And that ends up being 0.3125. Okay, what about the die part? So 5 or 6 comes up exactly twice in 4 rolls. Okay, so we are choosing 2 rolls out of 4 that are going to have 5 or 6, and then the probability of these rolls that we chose is 1 over 3 squared. So that's where we got 5 or 6 times 2 over 3 squared, which is when we did not get 5 or 6. And this multiplies out to 0.2963. So tossing a coin like this is it's more probable to get 3 heads in 6 tosses than getting 5 or 6 exactly twice in 4 rolls. Another problem related to dice. So in this pair of loaded dice, a 4 appears on the first die with 2 over 7 probability, and a 3 appears on the second die also with 2 over 7 probability. All other values appear on each die with 1 over 7 probability. Now the question is, what is the probability of 7 appearing as the sum of the numbers when these 2 dice are rolled? So, what are the events when the sum is 7? We can easily list all of them. So these are all the possibilities when the sum is 7. And then we can calculate using the product rule the probability of each individual event. So to get 1,6, the probability is 1 over 7 squared. To get 6.1, 1 over 7 squared, and so on. The interesting one is 4,3 because this is the one where 4 appears on the first die and 3 appears on the second die. So that's 2 over 7 squared. We add this up, we get 9 over 49. And that's the solution for this problem. Okay. Okay, one more example problem. And here we're going to look at the expected values. So the question is, what is the expected number of times a 6 appears when a fair die is rolled 10 times? So here we should recall that if x denotes the number of successful trials in this experiment, then the expected value of x, which follows from the theorem of expected values, is equal to n times p, which is equal to 10 times 1 over 6, which is equal to 5 over 3. So, as I stressed out before, if we know how to apply this theorem, we can compute these values in a very short amount of time, as opposed to doing the long computation involving Bernoulli trials and so on. So make sure to learn how to apply this theorem. Okay, the following problem asks us what is the probability that exactly 4 heads appear when a fair coin is flipped 5 times, given that the first flip came up as heads. So we are looking at a setup where we have heads come up during the first toss or first flip, and then we have to fill in the other 4 slots. And now the question is, what is the probability that heads appears in 3 of the last 4 slots? So we've did similar problems before. So we have to place 3 heads in these 4 slots, and the probability of each of these is then 1 over 2 to the power of 4, because it's a fair coin. And when you calculate this out, you get the total probability as 1 over 4.